Alright, so I'm going to do 6.2 this morning. It should be not a horrible section. I'll just kind of jump right into it. The first four problems give us pictures of functions. They're functions because they pass the vertical line test for both the graphs. If you draw vertical lines, it's impossible to draw a vertical line to touch the graph more than once. So that makes them functions. And then once we have functions, we have two styles of functions. We have one-to-one functions and then not one-to-one functions, which is maybe not the best name, but it's what I call them. To be a one-to-one function, you have to quote-unquote pass the vertical line test, horizontal line test. Meaning that it's impossible to draw a horizontal line to touch the graph in more than one place. I'll read this again just in case you can't read this. So to be considered a one-to-one function, you have to pass the horizontal line test, which means it's impossible to draw a horizontal line to touch the graph in more than one place. To be a not one-to-one function, you have to fail the horizontal line test. Which means it's possible to draw a horizontal line to touch the graph in more than one place. So when I look at the graphs of problems 2 and 4, problem 4, because it is possible to draw a horizontal line parallel to the x-axis and touch the graph more than once, we say that number 4 is not a one-to-one function because it fails the horizontal line test. On the other hand, problem 2, no matter which horizontal line I draw, it's only going to touch the graph once. So it passes the horizontal line test, and this is one-to-one. Those are the friendly problems 1, 2, 3, and 4 because it gives me the graph. The next group of problems asks me to create a graph. I know that the next group of problems don't make it on the test, but they're worth seeing if you're taking Math 151 next semester. If this is your last math class or going on to Math 142, skip the next problems because they're not going to be on the test, but they are going to maybe help explain the third group of problems, but you probably can get by with the third group of problems without watching it. But if you're going to college algebra, you should definitely watch these. So 5 through 12, I need to also determine if the function is one-to-one or not. But I'm not given a graph, I'm given an equation of a function and either a table of values to use or a common enough function that I should know how to graph it. So for each of the problems between 6 and 12, I'm going to sketch a graph. I'm going to look at the graph and decide whether the function's one-to-one or not. And then somewheres I'm going to make some comments about if we don't have a graph and we have points, how can we tell if a function's one-to-one or not? When when I'm dealing with function notation, if you don't like it, you can change the function notation to a y. So if I wanted to sketch a graph for number 6 and the function notation was kind of messing me up, the graph of g of x equals x plus 3 will be the same as the graph of y equals x plus 3. For me, it's just easier to graph with y's, so I'm going to graph with y's. And immediately, I don't see an x squared. I know this is going to graph to be a line. This is in the form y equals mx plus b, where the m is the number to the left of the x. I don't see a number to the left of the x, but I know it's a 1. And I'm going to even emphasize more it as a fraction. It's 1 over 1. And the b is 3. So I can graph this without even making a table of values. Lines are the easiest things for me to graph. I plot the b on the y-axis, and then I use the slope to finish out my graph. So I'm going to go up 1, right 1. I'm going to draw a line, because I know that this is a graph of a line. So that's the first thing I needed to do for all the problems between 5 and 12, is sketch a graph. And I said you may construct a table of values or use a technique you've already learned. So I used a technique that we learned in chapter 3 on how to graph a line. And now I'm going to determine whether the function is 1-to-1 or not 1-to-1. I look at the graph. This graph is going to pass the horizontal line test. No matter where I draw a horizontal line, it will only touch the graph once. So this is 1-to-1. I'll just say it's 1-to-1. So for each of the problems between 5 and 12, I'm going to sketch a graph, and then I'm going to comment on either I'll say it's 1-to-1 or not 1-to-1, because that's the two things that need to be done for 5 through 12. That's the easiest problem, because lines are easy for me to graph. 8's not as easy, but still not that hard for me. 8, since we just came out of chapter 5, you should recognize that to be a parabola because of the parentheses with the x squared term. And when we're graphing parabolas, we make a table of values, and we change the sign of the number inside the parentheses, put that in the middle of the table, and now I'm going to get a table of values. So I'll get some y's. So turn my calculator on. Mode 7, parentheses, alpha x minus 3 squared plus 6. Table start 1, table end 5, step 1. And I get 10, 1 comma 10, 2 comma 7, 3 comma 6, 4 comma 7, 5 comma 10. So I'll plot those points. You know, it's not going to be a stellar job plotting the points, but it's going to be good enough. So first I see the point 110, then the point 27, then the point 36, then the point 47, and then lastly the point 510. I knew this was going to be a parabola. So I've done the first part, the sketch a graph, because the instructions asked me to do two things: sketch a graph. Now I need to determine whether the function's 1-to-1 or not. This is clearly not 1-to-1. It's going to fail the horizontal line test. But I need to illustrate something when I draw my horizontal line that's going to be important. You'll notice that this graph, if I drew these points right, this definitely is not 1-to-1 because it goes through the graph twice on a horizontal line. I could tell without graphing that this was going to be 1-to-1 if there are points that have the same y, like those 2 points or these 2 points. Then a horizontal line drawn through those 2 points are it's gonna touch. So if I didn't have a graph and I just had a set of points, a graph is not 1-to-1 if there's duplicate y's. It is 1-to-1 if all the y's are different. So this is going to be important for the next group of problems. So without a graph, I can tell if a function is 1-to-1 without a graph, if I know all of the function's points, at least some of the function's points. All would be nice. But sometimes we just can't know them all. So we'd say if I didn't have the graph and I just had the points, it's not 1-to-1 if there's duplicate y's. This is going to be important in the next group of problems, so you need to get this into your notes or into your heads. And you can see these lines that go through the points that have the same y's. The line that goes through the points that has the same y's is a horizontal line that touches a graph more than once. And we'd say if we don't have a graph but we have points, it is 1-to-1 if all the y's are different. That again, this little couple sentences here is going to be important after we get out of these graphing problems. So I can tell if a function is 1-to-1 even if I don't have a graph, if I know all the function's points. A function's not 1-to-1 if there's duplicate y's in the listing of points. It is 1-to-1 if all the y's are different. I'm going to graph number 10, and in general I might not know what the shape of number 10 is going to be, and it's more of an advanced graphing problem in general, but I gave you a nice hint. I said if you use this table will produce a good enough graph, and that's kind of the trick to graphing when you don't have a lot of techniques that you might learn in college algebra or calculus. If you can get a starting table that's reasonable, then you can generally produce a pretty good graph. Again, I don't like the function notation when I'm graphing too terribly much, so I'm going to think of this as a y. So I'm going to have an x column and a y column. Had I not told you to use these points, and you just randomly picked points by yourself, you might not get a good representation of the graph from your table. And when you get higher in math, you'll learn different strategies for making good graphs when you're not sure what the picture's going to look like. A lot of times x to the 4th problems kind of look like parabolas with little flatter bottoms. So let me graph this. I'm going to go mode 7 for table. I don't think I need this x to the 4th in the parentheses, so alpha x up arrow 4 minus 3, start at -2, end at 2, step 1, and then I see -2, positive 13, -1, -2, 0, -3, 1, -2, and 2, 13. So even without doing a graph, I know I'm going to say this is not 1-to-1 because I have duplicate y's. So my graph is going to fail the horizontal line test. So this is not a 1-to-1 function. I'm not going to graph these terribly well. I'm going to go 5, 10, 15, and then -2, 13, -1, -2. I'm going to go down here at -5. So -1, -2, I'm going to call that point. 0, -3, I'm going to call that point. 1, negative 2, I'm going to call that point, and then positive 2, 13, I'm going to call this point. And I start to see a parabola again. They don't have to be parabolas, these x to the fourth, but a lot of times they kind of have that shape. It's just the bottom is a little bit flatter than a parabola's bottom. So I've sketched a graph, and again, I can see that it's not one-to-one. And real specifically, the points that I have with the same y's, a horizontal line through those points is going to touch the graph more than once, and that's going to make it fail the horizontal line test. So even had I not graphed, I could have told you this was not one-to-one because of the duplication in the y's. I'm going to do number 12 now. And I said use the same starting table. Cubes can look very different than fourth powers. I don't expect my graph to look the same at all. Again, this is not really the focus of this chapter. And I don't think I'm going to have you graph and determine one-to-one on the test. So I'm going to use this table of values because I decided for you that it was going to at least give me a decent picture. So I'm going to go mode table alpha x cubed minus 2, start at negative 2, end at 2, step 1. So I get negative 2, negative 10, negative 1, negative 3, 0, negative 2, 1, negative 1, and 2, 6. So I suspect that this is going to be one-to-one because there's no duplication in the y column. So my best guess is this should be one-to-one as opposed to not one-to-one. Let me sketch a graph on my graph paper. So I'm going to plot these points on this graph paper. So the first point I'm going to plot is negative 2, negative 10. And then I'm going to plot the point negative 1, negative 3. Then I'm going to plot the point 0, negative 2. Then I'm going to plot the point 1, negative 1. And then I'm going to plot the point 2, 6. And I'm just going to connect the points with just how they kind of point me. So the graph should look something like that. That's a pretty common shape for an x cubed graph. And you should tell that it's going to pass the horizontal line test. It's impossible for me to draw a horizontal line to touch the graph in more than one place. And in order for it to fail the horizontal line test, I need 2 points with the same y's. And since all the y's were different in my table, I suspected the graph was going to be one-to-one. All right, so that bank of problems, the 5 through 12, more than likely aren't going to make their way onto the test. The next bank of problems do make their way onto the test, and they have a little extra level of complexity, I guess. So the next problems, 13 through 18, they give me functions defined as points. They're functions because all their x's are different. If you had duplicate x's, you wouldn't have a function. But in the world of functions, there's one-to-one functions and not one-to-one functions. The first thing I need to figure out is if the given function is one-to-one or not. If it's one-to-one, I have to do something called find its inverse. If it's not one-to-one, it stops. So for these problems, you're either going to say it's one-to-one, and then if it's one-to-one, I'm going to find something called the inverse. I'm going to find the function's inverse. I'll talk about that when it's important. So that's one thing I might do for these problems. And then if I say the problem is not one-to-one, if I determine that, I stop. So I'm not going to do the odd problems, I'll just do the even problems. So if I look at problem 14, I don't have a picture, but I have a set of points. If I look at the second point and the fourth point, those points have the same y's, that means that function is not one-to-one. Because if you have duplication in the y's and you graph those points will lie in the same horizontal line. So for problem 14, I'm going to say this is not one-to-one and stop. If it was one-to-one, then I'd need to talk about the new concept in 13 through 18, the inverse of a function. But since it's not one-to-one, I just stop. When I move on to 16, I look at this function because all the x's are different. I see that y of 4, y of 6, y of negative 3, and y of 0. Because all the y's are different, this function is one-to-one. So because it is one-to-one, I need to do the extra. I need to find the inverse. So I'm going to write the inverse of k is, I'm going to use the same notation. And to create an inverse of a one-to-one function, it's super easy when the function is written as a set of points. You just switch the x's and y's for each point. So the first point in the original function is negative 3, 4. In the inverse of it, you get the point 4, negative 3. The second point in k was negative 5, 6. In the inverse of k, it's going to be the point 6, negative 5. And then similarly, I'm going to have the point negative 3, positive 9, and 0, 4. So the inverse of a one-to-one function defined as a set of points you can create by just switching the points. You don't switch any of the signs, you just switch the x and y's and you're done. This is not how I'd show the answer in the back of the book. So this symbol k with a negative 1 exponent, that negative 1 exponent in function notation means the inverse of. So that symbol means the inverse of k. Doesn't really have the is. So I said that it's one-to-one. I told you what the inverse is. A mathematician wouldn't write this. A mathematician would say the inverse of k is, and use an equals for the is, and then do the same points. So this is a mathematical shorthand that has the same meaning as what I wrote directly above it in a little almost sentence. So this symbol and these words mean the same. So the symbol, a function name with a negative 1 exponent, in function notation, the negative 1 exponent means the inverse of, and then whatever the function name is. 18 is kind of a strange function, but if I look at the y's are 1, 2, 4, and 5. So n is a one-to-one function because all the y's are different. So because it is one-to-one, the instruction said if it is one-to-one, if it's not one-to-one, stop. If it is one-to-one, find its inverse. So I'm going to find its inverse. And if I'm slick, I do this. I go, and the inverse of n is, it's not going to look too much different because when I switch the points, because the x's and y's are duplicated, and on most of the points, the only point that's going to look different is the third point. This is the only point that you can tell that I've switched the x's and y's. This is the best answer. If you want it to, instead of using the symbol, you can say the inverse of n is, and then write the same stuff. But in most math books, in fact, you're going to see the negative 1 exponent notation to mean inverse rather than using the words. So this symbol, n with a negative 1 exponent, it means, it's a shorthand for the inverse of n. So immediately when I see a function name with a -1 exponent, I don't think fraction, I think the words the inverse of and then whatever the function name is. So far we haven't done a heck of a lot of algebra. The last group of problems in this section are where the algebra exists, and the ones that are test-worthy are the ones that don't have exponents or are radicals. So once I get beyond once I get to problem 26 where I see a cubed root, that's not going to be test-worthy, but I'm going to do them just so you can see them, because these come back up again in college algebra, and it can't hurt to see them first, a second time. You'll do better if you see them a second time. So this, if I graphed it, was going to be a one-to-one function. It graphs to be a line. So the instructions say don't even bother determining if these are one-to-one. They are one-to-one. What I want you to do is find the inverse and express it with the inverse notation with the -1 exponent. So I need to get the steps to find an inverse of a function. So steps to find the inverse. And it has to be of a one-to-one function. If you use a not one-to-one function, the inverse isn't a function. So I go through just a few steps. They're real easy. First step that I always do is that I'm given function notation it's hard for me to work with. Temporarily, I'm going to change the function notation to the letter y. Eventually, I'm going to go back into function notation on my last step. So to find the inverse of a one-to-one function, you switch the x's and y's. If you don't see both an x and a y, it makes it hard to do that. So I change the function symbol to a y. That's completely legal to do. I do that a lot. The second thing I do is actually create the inverse. How do you create an inverse of a one-to-one function? You switch the x and y. Then I technically have an inverse. It's just not written in the most desirable form. So this was my step 1. My step 2 is I'm switching the x and y. That's actually creating an inverse. Step 3 is to solve for y. So I'm going to add 6 and divide by 3. When I add 6, I get x plus 6 on the left side, 3y on the right side, and then I'm going to divide by 3 in a way that I think I'll make less mistakes. So I'm going to divide everything by 3. The x over 3, you can leave it as x over 3, or you can write it as 1/3 x. You can bring the x to the right of the fraction and put a 1 in the numerator. So I can write x over 3 plus 2 equals to y. It's also okay to write 1/3 x plus 2 equals to y. And I would always write my answer like this, x over 3. But it is legal when you have an x in the numerator of a fraction to just bring that x out front and leave a 1 behind. So I'm almost done. Now I need to get rid of that y. And I'm going to replace the y with an inverse symbol. I'm going to write my answer. So my answer to this problem, and usually you write the function notation on the left, and to a mathematician would read this, the inverse of f, and then the equals means is, and then x over 3 plus 2, or if you like the other version. Again, a mathematician would read this as the inverse of f of x, the equals is, and then x over 3 plus 2. So that's what this answer means. And when I see this notation, I know that this function has been created from the f function, and I created it by switching the x's and y's, because immediately when I see that symbol, I know I'm switching x's and y's. Okay, so I'm going to do 22, 24, 26, and 28, doing exactly these steps. Change the letter to y from the function symbol, switch the x and the y, do the algebra to solve for y, and then replace the y with the inverse symbol. So for problem 22, if I want to follow these steps, first step, I'm going to change the function notation to the letter y. So I'm going to write y equals 2x minus 5 over 7. That's an easy step. Second step is also an easy step. Switch the x and y. I get x equals 2y minus 5 over 7. The thing that makes these problems hard for some students is they just don't know which algebra strategy to use to do the step 3 solving for the y. For me, this one's just kind of crying out cross-multiplying. The only kinds of problems that you'll get on the test are like 20, 22, and 24. So just need to get these lines down. They're all lines because they don't have any x squareds. You don't have to worry so much about the cube roots and the third powers. So the strategies for solving for y are going to be what I did for the last problem, or cross-multiplying when we get to the test questions. So I'm going to set this up for cross-multiplying. And it doesn't matter when I cross-multiply what side I put things on. So the cross-multiplying here is going to be 1 times 2y minus 5 equals x times 7. The 1 times 2y minus 5 I write as 2y minus 5. The x times 7 I write as 7x. I'm almost done solving it for y now. It looks just like kind of the last problem. So I'm going to add 5 and divide by 2. When I add 5, I get 2y equals 7x plus 5. It's safest just to divide everything by 2, even though nothing's going to reduce. I'm going to get y equals 7x over 2 plus 5 halves. The 7x over 2, I could bring the x out front. I could have written y equals to 7 halves x plus 5 halves. Both of those are considered done with step 3, solve for y. Now I'm going to replace the y with the inverse symbol. I want something to say the inverse of g of x is, so I'm going to use the g symbol. And here's going to write my answer now. So I'm going to write the g symbol. The negative 1 exponent translates to the inverse of g of x. The equal sign gives me is, and then whichever one of the two answers above it I want. It doesn't matter which. And there are other forms of the answer that are okay. I've just had best success sticking to this form of the answer. Again, a mathematician would read this answer as the inverse of g of x. The equal sign is, and then 7x over 2 plus 5 over 2. So this is also test worthy, as was problem 20, and is problem 24. So for problem 24, the inverse is kind of surprising. It's rare, but it can happen that a function is its own inverse, which is really odd. But I'll show you the algebra. So step 1, to find an inverse of a 1-to-1 function, change the function symbol to the letter y. Easy enough. Step 2, create the inverse by switching the x and the y. Step 3 is where it gets hard sometimes, solving for y. And this one looks again to me like something to solve by cross-multiplying. So I'm going to go x over 1 equals 3 over y. And I'm going to cross-multiply down and up. I get x times y equals 1 times 3. So that gives me x times y equal to 3. I'm not solving for y if I stop here, so I divide both sides by x. On the left side, my x's cancel. I'm left with the y. On the right side, I have 3 over x. I've finished my step 3 solving for y. Now I want to replace the y with the inverse symbol. Since the letter in this problem is h, I'm going to say the inverse of h is, and then just the 3 over x. This is a rare function that is its own inverse. Again, somebody that reads mathematics would read this as the inverse of h of x is, and they would know that this function was created from that h of x function by switching the x's and y's. So the next few problems are, again, if you're going on to Math 151 next, kind of important to watch. If you're not going on to Math 151 next, and 26 and 28 aren't something you'd see in 142, and not something that I'm going to test on. So, but if you're going on, it's good to watch. So it's not that hard either. So first thing, change the function symbol to a y. So I get y equals the cube root of x minus 2. Step 2, create the inverse by switching the x and y. X equals the cube root of y minus 2. The solving for y, hopefully you can tell how to do it. I'm going to cube both sides to get rid of the cube root. On the left side, when you cube the x, it just stays x cubed. On the right side, when you cube a cube root, you cancel out the cube root symbol, leave yourself what's under the cube root. In that case, it's a y minus 2. And I'm just going to add 2 to both sides. I'm going to be done solving for y. I'm going to get x cubed plus 2 on one side, y on the other. I'm done solving for y. Now I'm going to replace the y with an inverse symbol. So I'm going to say the inverse of m is x cubed plus 2. Do a lot of inverses in college algebra, so it's good to get good at them. One more problem. Again, I can't ever remember putting a cubed root problem or x cubed problem on a test in terms of finding an inverse by hand. That's a little, I don't know that it's too advanced for a college algebra class, intermediate algebra class, but I never put them on. So 28, find an inverse by hand. Step 1, change the function symbol to a y. I get y equals x cubed minus 3. Step 2, switch the x and y. I get x equals y cubed minus 3. Step 3, solve for y. I'm going to add 3 to both sides and get x plus 3 equals y cubed. To get rid of an exponent of 3, you have to cube root. So I'm going to cube root the left side and cube root the right side. Cube rooting cancels out an exponent of 3 and leaves me with the y isolated on the right side. You don't do plus or minus when you do cube roots, you just do plus or minus with square roots. I've solved for y. Now I'm going to replace the y with an inverse symbol. I'm going to write the inverse of f of x is cube root of x plus 3. Again, this symbol, I read this as the inverse of f of x, and then the equal sign is my is, and then what the answer is. And that, again, that's the cube root of x plus 3. So that's the whole section. Felt like a short section. 6-3 is also, I think, a shortest section. We get a few short sections. 6-7 is monstrously long, so it'll make up for it, I guess, when we get there. All right, so I'm going to shut this down, and hopefully you feel good about this section.